In this video, we're going to take a look at first order partial derivatives using the chain rule, and then we're going to start to say, okay, well, what do second order partial derivatives look like? So here I have a function of two variables, z equals f of xy, and here we have x squared plus 2xy to the fifth power. I, first of all, would like to find the first order partial derivative with respect to x. So, okay, here I want the first order partial derivative with respect to x. So I'm treating y as a constant here, but I have perhaps a slight issue. Here I have x squared plus 2xy, which is a function of x, inside of this x to the fifth power right here. I actually have a function inside of a function. So this is going to require our chain rule. So perhaps we'll take a second to rewrite this. We'll say, okay, I'm going to pick that inside part just like I did with the chain rule before. U is equal to x squared plus 2xy. We say, okay, if we have u, we generally need u prime, but here u prime is not particularly clear since we have the partial with respect to x or the partial with respect to y. So instead, I'm going to write u sub x here, the partial with respect to x. So u sub x, this is, let's see, here derivative of x squared, that's just going to be 2x. Derivative of 2xy, remember we're just going to pretend like that y isn't there for right now. The derivative of 2x, that's just going to be plus 2 times, well, y is a constant multiple, so I just multiply the derivative by that, so times y. So here is the derivative of the inside part with respect to x. So I'm going to take a moment to rewrite this. This is f equals, I'm just going to write f. This is really, u to the fifth power. So when I take the partial derivative with respect to x, we'd say, okay, the derivative of this part right here, well, that's 5u to the fourth power times, normally we would say u prime, but we said, okay, instead we're going to say times u sub x, the partial derivative with respect to x. So now I just need to take my u and the derivative of u and plug those back in. So I'm just going to take these guys and plug those back in over here. So let's see, this is really 5 times x squared plus 2xy raised to the fourth power times u sub x. U sub x is 2x plus 2y. I would probably just leave my answer exactly like this. If you really wanted to, you could take this 5 and distribute it to these two terms over here. You cannot distribute it to these two terms right here because of this exponent of a 4, so just be very careful. Generally, I'm not really going to simplify these anymore. Similarly then, if I want the partial derivative with respect to y, it's going to be a very similar process here. So again, let's just write our function so that we have it in front of us. This is x squared plus 2xy raised to the fifth power. So again, I see this function here, which is x squared plus 2xy. As soon as you see that y, you know that we're going to have a chain rule here because it's inside of this x to the fifth power. So you may need to, if you need to, off to the side, say u, well, that's equal to that inside part, which again is x squared plus 2xy. And here, here I want the partial derivative of u with respect to y. So u sub y, x squared, that's a constant, so the derivative of x squared, that's going to be 0. Plus here, ignore 2x for a moment, the derivative of 2y, that's just going to be plus 2. And then that x, it's a constant multiple, so that just comes down to the next step, so 2x. So the partial derivative with respect to y is simply 2x. So if you need to, we can rewrite this. This is f equals u to the fifth power. So let's see, f sub y, this is 5u to the fourth power times u sub y. Notice that when you use the chain rule, the overall structure of these is going to be the same. The derivative of that u part doesn't actually change. It's the derivative of the inside part, u sub x versus u sub y. That's where the difference is going to happen. So here, 5 times u to the 4th, u was x squared plus 2xy raised to the 4th power times u sub y, that is just 2x. If you really wanted to, you could multiply 5 and 2x. You could say 10x. 10x times x squared plus 2xy to the 4th. I think either one of these is perfectly fine. Of course, you don't have to show all of this work. You can take, a little bit of a shortcut here. But this is, I just wanted to take this process, draw it out, just because this is a new idea, this applying the chain rule to functions of several variables is not something that we're used to dealing with. So take your time with these problems. There's probably only a couple in the homework exercises, but I think they're good practice. Oh boy, now we got to talk about second order partial derivatives. So there were 2 different first order partial derivatives that we could have. We could have the partial with respect to x, the partial with respect to y. There's 4 second order partial derivatives that we could have here. I could have the partial with respect to x, and then the partial with respect to x again. So this is the partial derivative with respect to x, and then the partial derivative with respect to x. F sub xy, so this is the partial derivative with respect to x, and then I change gears, I take the partial derivative with respect to y. I could switch them around. I could say yx, this is the partial with respect to y, and then the partial with respect to x. And then, of course, I could do y both times. This is the partial with respect to y and the partial with respect to y. So there's 4 different second order partial derivatives that we could have. So here I have a function. I'm going to work with these. Here, let's let z equal f of xy, and here my function is 3x squared minus 2xy cubed plus 1. So first I would like to find f sub xx. So before I can jump straight into the second derivative, I need the first order partial derivative as well. So I need, first of all, f sub x of xy. So let's take this one at a time. Derivative of 3x squared, that's going to be 6x. Derivative of negative 2xy cubed, remember, again, you can cover up that y, but derivative of negative 2x, that's going to be minus 2 times our constant multiple, which is y cubed. And then the derivative of 1, that's going to be 0, so we don't really need that. So here's our first order partial derivative. We need to basically just repeat that process one more time here. So if I want f sub x, xy, so this is the partial with respect to x, and then the partial with respect to x one more time. So let's see. Oops, you know what? Let me do this in a different color, just so that we don't get mixed up. So this will be f sub xx. So here, the derivative of 6x, well, that's just going to be 6. Here, the derivative of negative 2y cubed. Here, in this case, remember we're treating y as a constant. So this term right here, derivative of this term with respect to x, will simply just be 0. So 6 minus 0 gives me 6. So there is my second order partial derivative. So when I change gears now and I say, okay, now I want the first order partial with respect to x, and then the then the second order partial derivative with respect to y, I've already done part of this work. I actually already found the first order partial derivative with respect to x. So this is actually just going to come down here. F sub x, xy, is 6x minus 2y to the third. So now I've done the partial with respect to x. The only thing that remains now is the partial with respect to y. So I'll get my different color out. F sub xy, x comma y. So here, this time I'm treating I'm treating x as a constant. I want the derivative of y. So 6x, I'm treating that like it is a constant. The derivative of any constant is 0. Minus, over here, derivative of 2y to the third. That should be minus 6y squared using our power rule. So we have negative 6y squared. Next up, we want first the partial with respect to y, and then the partial with respect to x. So here I have a little bit more work to do this time, and actually I'm just gonna write my function over here just so that I have it, because I don't want to have to scroll back and forth. Let's see, 3x squared minus 2xy cubed plus 1. So all right, first I'm gonna take the partial with respect to y. And here, let's see, 3x squared, I'm going to treat that like it's a constant. Derivative of any constant is 0. So this is 0 minus, cover this x up if you need to, derivative of negative 2y to the third, that'll be negative 6y squared. But remember, this x is a constant multiple, which means we just multiply our derivative by x. So really all I have is negative 6xy squared. So there's my first derivative. Now I'm going to go find the second order. So this is f sub yx. And here I just want the derivative of this guy. There's only one term to work with. So here in this case, I'm going to treat y squared like it's a constant, pretend it's not there. Derivative of negative 6x, it's just negative 6. So negative 6 times y squared. Hey, look at this. Those two are the same. It turns out that this is a property of these two that I don't remember exactly the circumstances. It's not anything you need to know, but I think it's for continuous functions. If you're working with continuous functions, then this fact is true. You can reverse the order of the partial derivatives with respect to y and x and end up with the same thing. I don't want to say it's true for every single case. I believe it's true for continuous functions, which are functions that we'll be dealing with here. Lastly here, I want the partial with respect to y and then the partial with respect to y one more time. So let's see, f sub y. Actually here, let's do this. Let's just bring this guy down. So let's see, we said this ended up as negative 6xy squared. If I want the partial derivative with respect to y again, here I should have minus 12xy. So here is my last second order partial derivative. Notice here, negative 12xy, that absolutely does not match the second order partial derivative with respect to x of 6. So just be careful. The two middle ones will usually match up, but that is not true for f sub xx and f sub yy. These two will not be the same. All right, let's look at one last example for our class here. Here I have an exponential function. I have e to the 3x plus 2y power. So hopefully you look at this and say, hey, I've got this function here of x and y, 3x plus 2y, inside of this exponential function. When I take the derivative, I'm going to have to use the chain rule. So here, I'm going to go through this relatively quickly. If I want the first order partial derivative, and actually here, we'll do the first one. We'll draw it all out. So we should start by finding f sub y, but before we do that, we may want to rewrite that. We may want to say, okay, here is u is just the inside function, which would be 3x plus 2y. First, I want the partial with respect to y, so u sub y. In this case, would just be 2. So f my original function I can think about as e to the u. So if I want f sub y, this is really equal to e to the u times u sub y. And if you want to, I would go ahead and take u sub y and plug that back in. You can take u and plug that in as well. I don't think that's as necessary, and I'll explain why in just a second. So right now I have the first order partial derivative. This is equal to e to the 3x plus 2y times u sub y is 2. Maybe I'll rewrite that as 2e to the 3x plus 2y power. So here's my first order partial derivative. I want the second order partial derivative though. And here I see, okay, again I have 3x plus 2y, that's a function of both x and y, inside of the exponential function. It's another chain rule. U is actually not going to change though. U is actually still 3x plus 2y. U sub x here in this case, because now I want the partial with respect to x, is just 3. So if you need to, take a moment here and say, okay, f sub y, this is really equal to 2e to the u. So derivative of y, f sub yx, that's going to be 2e to the u times u sub x. So this is 2e to the 3x plus 2y times 3, or 6e to the 3x plus 2y power. So here's that second order partial derivative that I was looking for. This is f sub yx of xy. Holy moly. Let's look at one last second order partial derivative. And just to write our function here one more time, f of xy, we said that was e to the 3x plus 2y power. So here I want, first of all, the first order partial derivative with respect to x this time. So here I'm going to go a little bit quicker. So first I would say, okay, multiply by the power, right? I'm looking at this as e to the u. I know that the derivative of e to the u is really u prime times e to the u. If you want to use that shortcut, say the derivative of my power with respect to x, that's going to be 3e to the u, the power stays the same, so 3x plus 2y power. And then if I want to take the partial with respect to y now, f sub xy, x comma y, this part's going to stay almost identical, 3e to the 3x plus 2y power, but I need to multiply by that u prime, which in this case, I'm taking the partial derivative with respect to y. So the derivative of 3x plus 2y with respect to y, that's going to be 2. So 2 times 3, hey, there I have 6e to the 3x plus 2y power. I see once again, hey, that these two match up. That's awfully nice. Again, I won't say that will happen every single time, but it will happen the majority of the time. So I guess that's it. That's the end of business calculus. So at this point, I'll just say the end. I hope you've learned a little bit about calculus and a lot about yourselves along the way. I wish you all the best of luck in your future studies. If you have questions about this section or anything else going into the final exam, please feel free to email me. I'll do my best to get back to you as soon as I possibly can. But that's all I've got. Hope you guys take care out there.